Hello and welcome to Android Developers Backstage. I'm Tor and Norbye from the Android Studio team.
And I'm Romain from the Android Toolkit team.
We've had 2 guest plans fall apart this time. So it's just going to be the 2 of us, but we always have a couple of topics in our back pocket that we're particularly excited about. And so today it's going to be what?
Lint?
No.
You always want to talk about Lint.
Well, I got my way last time. This time we're going to do micro optimizations.
Yes, I was actually kind of shocked that you suggested that and not Lint.
Because I'm actually excited about it.
Okay, that's good.
Yeah.
And there's tooling involved, so that's good, I suppose, for you.
Yeah, and I think maybe this is something that is closer to us because we kind of went through, the bad old days.
Yeah.
And when you kind of had to care about this stuff. I don't just mean for you working on early Android with the hardware limitations. I'm thinking back to like the 80s, the VIC-20, the Commodore 64, when you discovered that if you wanted to build something good, it couldn't be in BASIC. You had to learn this thing called assembly code because that's how you could not just access the graphics, but also get the performance you had to, or it just wouldn't work.
Right, and even in assembly code, you have to be careful about not doing a division, for instance, because that was too expensive. Or
yeah. So having gone through that, I think it's a habit that you kind of get and you kind of stick with.
Yeah, it's interesting because this habit of optimizing at a low level, even when it's still useful today. It's still very useful today. But sometimes I catch myself when I'm writing code, automatically doing some of those optimizations, and I have to stop and take a step back and be like, no, I don't need to do this here. It's okay. For instance, if I'm building a desktop app that doesn't require high performance, just don't.
Take it from me, some desktop apps, if you don't care about performance, let's say that the name of the desktop app is Android Studio. Performance is going to matter a lot because we have a lot of users, on particularly slower hardware. And so I think obviously, all performance work should start with a profiler. You should definitely address the true bottlenecks first.
Absolutely.
But I feel like small things like setting initial sizes on collections is just a good idea. It's going to matter. I mean, especially on mobile, where even if the phone is fast enough, you just want to do less so that you're drawing less power, right? Even if the phone is fast enough, you want to maximize that battery life. So why cause a list as you're adding to it to have to keep resizing it and copying all the elements and rehashing all the hash keys and all that.
Especially in that case when it's the kind of optimizations that don't make the code harder to read or harder to maintain, there's no reason not to do it, I would say.
Yeah. And maybe this is also the old school thing, right? Where when I see, this is not going to sound like newfangled code at this point because everyone's used Java streams for years. But for a while, when I kept seeing the .stream, .collect, that thing was to me not easier to read in a good old for loop.
It's interesting because sometimes it is and sometimes it's not, right? I've seen, when you start chaining a lot of those operators, it becomes difficult to understand what exactly is going on. I mean, just like any piece of complex code, there's no secret.
Yeah, and I think that's a good transition actually to what we wanted to talk about, which is your Kotlin Explorer, because with Kotlin, there are these nice language primitives that you can use. And the amazing thing is that when you look at what the code does, it actually compiles down to the fast code that you would have written in Java. So you can write code using lambdas, for example, right? And inline functions, and it just actually will turn into beautifully optimized code the way you would have written. So you get nicer code, but the same performance. But every now and then, you do one small thing, and now the code is not the good.
And that's the problem with any high-level language, right? Because you're so far removed from the actual code that ends up running on the CPU, sometimes, yes, the compilers, the runtime will do exactly what you want, and they'll be super smart and optimize the heck out of the code. But sometimes you do something that looks very innocent and it's not doing what you thought it was doing and it's more expensive than it should be. But Kotlin is also interesting in the sense that the language itself has multiple facilities that do help you write highly efficient code that's still macro-optimized.
You're talking about value classes.
Value class is an example, but being able to create, operators, type aliases, extension functions, the fact that you can create extension functions on primitive types, for instance. So, to go into details, there's this piece of code, this kind of hash map that we use where, long story short, internally it stores bytes in longs. And basically, at some point, you need to iterate over specific bytes inside the long. the way this code is written is it uses extension functions so that you treat the long almost as an object, and so you can write your code as like an iterator. You can say, while the long dot has next, the long dot next, and you get the next byte that you're looking for. And when you read the code, you don't even realize that you're dealing with primitive types. It looks like fancy objects, but under the hood, when you look at the compiled code, it's super optimized.
And this sounds to me like what we had before value classes. I think in the value class world, you would completely create a value class wrapping that long.
So yes and no. The problem is that one of the issues with value classes is that you can't easily reassign them to themselves. Like if you need to change the internal value. For instance, if you have an array, you can wrap an array with a value class, but if you need to reallocate the array for whatever reason, that won't work. Like you can't do that. So they have limitations, but yeah, they can be very helpful. But the problem is that even in value classes, and for those who don't know, value class, so it's a special class in Kotlin, especially the inline value classes. They wrap a single type, for instance, an int or a long or a string.
Primitive.
Right. And the class itself goes away at runtime. So all the methods in the class are replaced with static methods that take the value that you're wrapping as a parameter. So they're as cheap as they can be. They're static invocations. It's the best thing you can do for the...
And it's really great for bit masks. So in Lint, I would find a way to talk about it. Lint has a concept of an API constraint. This idea that, hey, I've checked that the SDK int is at least 31, or hey, inside this switch clause or when clause, I've already checked for the values 1, 3, and 5. So we know it's not one of those, but it could be 2, 4, 6, 8 and above, right? That is represented as a API constraint. And we were able to implement that just by using a massive bit mask.
Right.
And so it's really very cheap to have these and pass them around because it's used everywhere. But at the same time, you got a nice object abstraction, right? You can pass this around, and to a casual observer, you just think it's an object. It's only if you try to do something like adding an extra, field into that API, into the value class, you'll discover that can't.
Yeah, and it's an object without allocations, right? Which is key. And we used inline value classes quite a bit in Compose. So for instance, if you're familiar with Compose, the types like size or offset that are used all over the place for drawing, for layout, are value classes. So the way we use them, like offset is a pair of x, y coordinates. So it's a value class that wraps a long, so 64 bits. And we use 32-bit for the x coordinate and 32-bit for the y coordinate. So when you access the x and y values, we just extract them from that long. But that's where it becomes interesting, because we did a bunch of optimizations in that offset class, because while we're wrapping the primitive type, and it's efficient and we're not allocating, handling this encoding and decoding properly, I ran into interesting things that were happening with the Kotlin standard library and the Kotlin compiler, and the code was not as efficient as it could have been. That's where I started doing a lot of macro optimizations because that code is used, offset is used all over the place. So being able to optimize it actually had an impact on the benchmarks we have for layout and rendering.
Yeah. I think this is also something where the fact that you are now in a Kotlin only toolkit and you're writing new APIs gives you that freedom. Like if you had to deal with Java, you probably wouldn't use value classes, right? And
I mean, you could, but I guess I've never tried to use value classes from Java because you have static methods, but I think some of them have mangled names, so I'm not even sure you can use them. So yeah, you probably wouldn't. And besides, the API would look out of place, I suppose, in Java.
I think even in the old Vue framework, right, you have methods that are returning objects, so you're kind of out of luck. Whereas here, you're building a brand new toolkit, Compose. Well, you can right up front decide, hey, we shouldn't be passing back objects. Yeah. And I'm assuming that was part of the design.
That was part of the design, very early on, because Compose targets all the way back to API 21, and those devices that came out back then are not the fastest today, and even today, there are low-end devices that. And
even not we've heard a couple of years ago that people were not adopting Compose because of performance regressions, because you went from a bundled toolkit to one that had to be completely initialized by every app and bundled with each app. And so performance was something you had to care about. You couldn't say, well, Art will take care of it. Well, phones are fast
Well, not
today.
only that, but also the existing Turkey, the view system, we spent over 15 years optimizing everything we could out of it. And it was written originally so the original device that we were working on was an 80 megahertz CPU, single core, no GPU. So that was the target for the code back then. And we didn't have a JIT. So
And you were famously not using enums, right? You were famously already being really stingy and trying to make sure, you had those bit masks. If you ever look at Vue.java, there's like mask 1, mask 2, mask 3. There's like all these bits we need. We're running out of bits. Let's just add another one. And so it was definitely performance tuned very heavily.
Right. And so, and when we compare Compose to Views, like Compose can be faster than Views in a lot of situations, sometimes as fast, sometimes a bit slower. It depends. The two systems are very different. So some things will never be exactly the same. But part of it is because, the Vue system was optimized as much as possible.
Yeah, that reminded me. So you gave a talk.
Android makers, in April. It was in April, I think.
Yeah, and one of the points you made early on was, hey, you have this loop, and you're iterating, over the columns and then the rows.
Oh yeah, so there was an actual piece of code that was in the testing framework for Compose, I think. Basically, we were doing image comparisons, or at least looking at the content of bitmaps, and there was a very, very simple mistake in there, which was iterating over the X coordinates first, so column by column, and then over the Y coordinates, so row by row. The problem is that bitmaps, the way they're stored in memory, they're stored row by row. So if you access the columns first, you're going to thrash the memory cache, the data cache on the CPU. And so just swapping the two loops, moving the Y loop first and the X loop second, I think that was a 2 or 4x speed up, something like that.
And I think it's a good example because it's one of those things where there are a lot of people who are like, don't worry about these things. Use whatever you want. The compiler and runtime will figure, don't fight art, don't fight the compiler, let it do its thing. And this is a domain specific thing. Understanding that the nesting of your operators, understanding how the bitmap that you're referencing very indirectly is laid out and how that affects the cache, which is very close to the hardware. I mean, you benchmark this on specific hardware. This is the kind of thing that the runtime can't understand for you.
Well, not only that, but I think, so if we take a step back, what's really important to understand when you write Java code or Kotlin code is that both Java-C, more Java-C than Kotlin-C, but Java-C and Kotlin-C are not compilers that are designed to perform optimizations. Because and we're talking here when you target, Android, for instance, or Kotlin JVM with Kotlin. So let's forget about Kotlin native and all that. Because you're in a world where the output of those compilers will be fed to a JIT or an ahead-of-time compiler. So the thinking, and it makes sense to say, okay, let's not bother with anything beyond basic optimizations. Like if you write if false, that's going to be removed at compile time. That makes sense. Inlining constants, fine. But anything else, really, those compilers won't do it for you because that's the job of the JIT and the ahead-of-time compiler. And the reason why they do this is because the JIT will have access to more information at runtime and can actually do more interesting things in some cases. So if you look at the bytecode generated by Java-C or Kotlin-C, again, Java-C being easier to look at, it's very close, very, very close to the original source code. And that's why you find so many decompilers, right, where you can go back to Java or Kotlin source code because the compiled code is...
Well, I mean, it's not only that. It's that it also makes the debugging experience much better.
And there's that as well.
We've discovered that, when you debug on Android in Android Studio, some of the behavior is counterintuitive because they've done too much optimization. So some of these trampolines you want to step at doesn't exist because it realized these two things are similar. I'm gonna merge them.
Just ran into that this morning.
Yes, it's kind of tricky, and it's because historically, back in the C and C++ days, we all used -G for debugging information and -X04 to optimize. In Java, you just tended not to do that.
Yeah, I think -G exists in Java-C. All it does is remove or preserves the line numbers, and that's basically the only thing it does.
So you didn't have that habit of super optimizing because it was kind of delayed for the runtime machinery.
But so in the world of Android, so what happens? So you have Java-C and Kotlin-C. Again, they won't do much for you. They will do very little. Kotlin-C a bit more, but it's not very important. But then there are other compilers in the mix. If you use R8 will do a lot of optimizations. but not all of them. But
and it's a kind of a funny compiler because it doesn't work on your source code. It's like post-processing, and it's going from bytecode to dex code.
Right, and in the process, it will do optimizations. And some of the optimizations it can do are amazing, right? There's inlining. I've seen it remove array allocations when it can, but it has limits to what it can do because of the semantics of Java and Kotlin. And then after that, like I mentioned earlier, you have the JIT or you have the AOT compiler, and those will do further optimizations, and some of them will be incredibly complex, and right as well.
And that's because they have access to actual hardware that they're running on.
Right. Yeah, because those are the ones that target the actual machine code that's going to be run.
Yeah, R8 doesn't know which kind of chip you're on.
Right. And then if we want to go further, it's interesting because, I think for a lot of us, assembly, ARM64, for instance, is like the final step. But no, because modern CPUs, they don't really run those instructions. There's microcode, so a lot of the instructions, or maybe all of them, I don't know, turn actually into microcode instructions, and understanding that, I'm sure, can be super helpful. But you gotta stop somewhere, right? But the point is, like, there's a chain of compilers, and understanding what they do can be really useful in guiding you in how you can write your Kotlin code to make it more efficient while maintaining, readability to some extent.
Yeah, I mean, what I did when I learned Kotlin, and I was trying to figure out some recommendations for the team, what to do, what not to do, like by lazy, let's stay away from that one for now. So I used the built-in IntelliJ compiler, which shows you the bytecode that the corresponding Kotlin C corresponds to, and then the decompiler to go back to Java. But you've taken it a step further because, again, you want to know what the dex code is, you want to know what R8 is done to it.
Yeah, it's not just that. So the Kotlin decompiler that's in IntelliJ and Android Studio, I used it a lot as well. I have two issues with it. One is it often doesn't work. I'm not sure why, but very often, like, it will produce, it will just give up on the output. And then when folks use it to go back to Java source because it's easier to read, the problem is that you're not seeing. You're back to source code. So you're back to hiding some of the information that you're looking for. So I built this tool called Kotlin Explorer because I was doing a lot of this investigation of the bytecode, the dex, and then the ARM assembly code to validate optimizations or to find optimizations. And doing it by hand is possible, but it's very painful. So I built this tool called Kotlin Explorer. It's on GitHub. And you enter Kotlin source code, and it can show you the Java bytecode, the dex bytecode, and if you plug in a phone or an emulator, it will show you the ARM64 assembly code. And you can also enable R8 or not if you want, and you can see what happens when you turn on R8. And it can be very, impressive what happens when you turn on R8. I've been using that tool a lot, and what I've been doing to do optimizations in Compose, I start using the profilers, the memory, the memory tracker to find places in the code that look suspicious. Like, why are we spending so much time there? Why are we allocating so much in that spot? Then I find the code, I look at it, I put it in Kotlin Explorer, I look at the assembly code, I look at the dex bytecode, and I try to see what can we do to make it faster.
Yeah, I mean, one thing that struck me is that in your talk, you mentioned, hey, really good use for AI is to have the AI describe the assembly for you because it does a really good job with that.
Yeah, because assembly code is interesting because when you look at x86 or ARM64 assembly code, it's impressive looking. And it's tedious because every operation is, does something very, very specific. And there are hundreds of instructions. And if you don't know assembly, I don't know assembly, like, you end up like going to the documentation all the time. And it's complicated because some of the instructions have modifiers and it's hard to understand that from the documentation. So I found that something like Gemini is really good at. You give it a few lines of assembly code, you say, like, tell me what this does line by line. It will be very good at saying, okay, this instruction does that, the next line does this. It's really helpful.
And so far, you haven't had a lot of hallucinations. You haven't been like, that can't be right.
No, it has been very good. I think because it's so specific, like those instructions are so specific, and they're well known and well documented. I was thinking of integrating that in Kotlin Explorer so you could do it right from the tool. I think that would be super.
Or we can integrate Kotlin Explorer into Studio or IntelliJ. That seems like
that would be nice. Get on it, Tor. And so while, once I had the tool, and that I think that speaks to the importance of, and it's nothing new, right? For engineers, like, we love building tools. But having this kind of capability, having this kind of view into the system, into what's happening, is immensely valuable. And it's funny because there are other existing tools that people know and hopefully love that were built for the same reason. Like Layout Inspector in Studio was born from Hierarchy Viewer. It's a tool I wrote, but that was born from another tool I wrote. So if we go all the way back to 2007, one of my first tasks on Android was to optimize layout and rendering. Because when I joined, when you did invalidate on a view, no matter what, you would always reinvalidate the tree and redraw everything. So the work was, okay, let's invalidate only when it needs to be. If things are already invalidated, and then when we go back down, let's redraw only what needs to be drawn. And to validate that the changes that we're making worked, I wrote that tool that basically captured a tree representation of the UI, and would capture a few frames, and then when I played it back, it would blink every node in a different color, saying like, this is invalidating, this is drawing, and I would be able to like visualize what's happening. And without it, like, yeah, life would have been hard.
Right.
So yeah, I think, and Lint, I think also came to be in similar ways. Like we're just trying to automate.
Well, you had written something called Layout Opt, which was a groovy tool, which just had some very simple rules around layout XML files. And I was like, well, let's build this into something a bit more formal.
Right, but the idea there was like, I was spending a lot of time explaining to various developers, like, hey, you should do this to make your layout faster. So it's like, let's build a tool. And then, you saw that, you're like, well, it could do so much more. Also be written in, not with regex and custom parsing.
Right, yeah. Yeah, I think that's a sign of programmers, right? It's to basically see something and go like, okay, we should write a tool for this. This is why I've been working on tools since.
Yeah, it's tough because it's often the question is like, okay, the task on hand, will I spend more time building the tool than doing the task by hand? Or, is it worth building the tool? And then the problem is that once you've built the tool, like with Kotlin Explorer, now I have folks who have feature requests and, and thankfully there's been like great contributions on GitHub, but now people want like, they want a Linux distribution and a Windows distribution. I'm like, I'm sorry, like I don't have time or the machines to take care of that. I wish I could, but it can't become a new job.
Yeah.
So yeah, it's always a fine line to walk.
Yeah,
right?
That's the temptation, right? Is that it kind of takes over and maintaining the tool becomes more of maintenance than actually utility you're getting from it.
Yeah, no, absolutely. But anyway, so once I had that tool, what was interesting is looking at code in Kotlin that looks innocent. There are some nasty surprises lurking in there, and some of them are not like on the face of it. They're not ridiculous. Like here's a good example. In Kotlin, there are those two functions called check and require. You just pass them a Boolean, so it's basically an assert, and you pass them a lambda that builds a string, right? So if it fails the test, it will call the lambda to get the string, and it will throw an exception with that string. That's great. And to avoid the lambda from being allocated, check and require are inline functions. Fantastic. At the call site, like the function call disappears and all that. The problem is that what it inlines in the end is an if statement. That's fine. But then inside the if statement, you have all the code required to build a string. So if you use string interpolation, that can be a lot of code. And then all the code to throw the exception. And in itself, that's not a big deal because you're going to, most of the time the condition will fail. You're never going to run that code. But that code needs to be loaded. And that code takes space in the instruction cache of the CPU. And so in some of those value classes we were talking about earlier, like size or offset, there were a lot of checks and require. And that was a massive amount of code that was never, ever really executed, but that was loaded, verified, taking place in the caches. Once I fixed that, we saw the benchmarks go faster. Again, because, this is a very specific piece of code that's used all over the place. We are a framework, so anything we can do to help the app is super useful, right? Like you probably don't need to worry about this.
Yeah.
But this is not something I would have thought about without being able to look at the final assembly and be like, oh, like here I'm literally extracting 32 bits from a float and I'm seeing like 500 instructions and this massive amount of code. So
you pull up the method and you're looking like, that's a lot of assembly.
Yeah, that doesn't make sense, right? And then you look at it, it's like, why do I see allocations? Why is there a bunch of jumps? And, it's like calling static functions, like what?
And this is one of those areas where it kind of goes a bit counterintuitive. You would think that inlining it should be fast, but the fact that there are
Not
these
always.
caches,
Mhm.
and if something is replicated a lot, well, that's actually bad.
And actually, recently I ran into this problem. I was talking to the with the art team because I have a case of there's a piece of code that gets inlined that I don't want to be inlined, and I can't get it to not be inlined, and it's really annoying me greatly. I'm trying a lot of tricks.
If system.getTime is less than put in some constant.
Yeah. And so there are other things that happen. For instance, I wrote a blog post about there was this method in Kotlin called char.isBlank. So it's a very simple function on the char type that tells you like, is this character a white space? Any white space. Or no, it's on string, I think, on char sequence. It checks every character. And you look at the code and it looks fine. There's like for each and there's a lambda and just test like, okay.
Well, it is an example of those abstractions that to some people are more readable. Like, oh yeah, look at that. We're doing if all it is char space, then you're good, right? And
right. Yeah, it wasn't a for each, right? He was calling the all function that takes a predicate.
And taking a lambda. So it's one of those like high level abstractions that's super clean. And again, most of the time that'll compile down to exactly the simple code you would think, a nice little for loop, right?
Except in the way it was written, what happened was it was using a variant of all that I think gives you a character instead of the index or something like that. Or no, it was giving you the index instead of the character. Anyway, there are two variants of all for a string, for a char sequence. And the implementation was picking the wrong one. And for those who are listening and not watching me, I'm doing air quotes. And what that would do is that the call side, because the method is inline, would end up creating an iterator, a range, there was a while loop. It was creating doing a ton of work.
Anytime you have those sequence operations and it is unable to turn it into a for loop, you end up with like creating iterators and
And turns out there's a variant of that all function. Again, I forget whether it's the one that gives you the index or the other one that doesn't do that. Why? I don't know. I don't understand Kotlin C. But unless you're looking at the bytecode, you won't be able to see that. And that was the root cause of a bunch of allocations in a particular piece of compose.
And like that's why you want a tool like Kotlin Explorer to understand that it takes just a small little tweak to that code that is normally performant for it to not be performant.
Yeah. And again, that's a problem with high-level languages, right? Like it's great that we should and we have to trust the compilers and the optimizers and so on, except sometimes they just won't do it for you and you can help them. And, that's a great example of like the code is still very readable, but, it's a lot faster and a lot nicer. So don't shy away from looking at...
we should have a tool that looks for these things and warns you. Maybe we could call it Lint. So actually, we do have some extra Lint checks in the AngularX code base, which is looking for things that you normally don't have to care about.
Yeah.
But we care.
Yeah.
And so we want to make sure that we aren't doing some of these things because these things are inlined and repeated and they're running in tight loops and that's where it matters.
Right. And again, like, you sometimes you're one character away. My favorite example, and it has been partially fixed, but over the years, when you do a for loop in Kotlin, it's you do like for I in 0.10. You look at the bytecode, it's exactly what you expect, increment a counter, and there's a goto and a condition. But then if you want to increment by 2 every time, so you do step 2, right? Mm-hmm. Just adding that step keyword, even if you say step 1, which should be the exact same thing, suddenly you're out of the happy path, and the compiler will create, I think it's called an int progression, and there's an int range, and so there's multiple allocations and method calls, and it's very expensive. And all you did was say like, I want to increment by 2. Like, that's surprising, right?
Yep. I do find myself missing the old Java for loop sometimes, with the initialization, condition, and increment.
Yeah, because then you have to go... Yeah, because the only way to fix that in Kotlin is you have to write a while loop and have your own counter, and it's kind of...
And I do like having that, being able to have it jump to the increment step.
Yes.
At the end. That's, you don't get that with while. So.
Yeah. And hopefully, at some point, like Kotlin C and the standard library will do all of that for you. But the point is like, Kotlin's been out for years and it makes perfect sense, right? Like they still have work to do.
As you know, I love Kotlin, but one thing I don't love is companion objects. Probably my favorite thing to hate on. And
Yes.
you touched on the real cost of companion objects.
Yeah. So yeah, companion objects are interesting because
And
they're
by the way, I didn't not like them because of the performance implications. This was just one more thing to add to my.
I hear you. I don't like them for the what's the word? Not the aesthetics, the ergonomics of them. Yeah. So it's interesting when you have a class and you add a companion object, it is represented literally internally as a static object. So then, as soon as you use the enclosing class, it has to initialize that class, which involves like resolving the static fields, which means initializing that object. So even if you create an empty companion object, almost, we won't go into too much detail, but almost every call site where you use that class, it will have to do, there will be extra code to make sure the class was properly initialized. And at every call site, for no reason. So if all you're putting in your companion object is a bunch of constants, you're paying a cost at every call site of your class. Almost, again, there's some trickery there for no reason.
Well, it was one of those things where you sometimes have methods that are not instance specific. So in the Java days, you would do static.
Yeah.
That makes sense. You're saying, hey, I have operations related to this class, but I want to not.
It's namespacing.
But it's not instance specific. And so you might think, oh, companion object is a good place for this, but there is a cost to that as opposed to making it top level.
There is a cost to that. I'm a big fan of top level functions, honestly. I know they have their own issues because they can be harder to find, and especially in the documentation, but I think I don't know, to me they're great because they're independent. I prefer static functions. But for instance, if all the constants that you're creating in the companion objects are private or internal, right? If they're not public, the namespacing is your problem. So just use a prefix in the name and make them top level constants. Like avoid completely the companion object. Yeah. Again, if it's a piece of code where performance matters and all that.
Yeah.
So you have to measure. And
speaking of we talked about the require and check a while ago, and one thing I really liked about Java was their assertion mechanism, because it wasn't just, as in Kotlin, a standard library function. It was actually a separate language concept.
Yeah, it's a keyword, right?
Not just a keyword. Like the JVM, when the assertions are off, will skip the bytecode.
Yeah.
So it's actually stripped. There's zero cost. It's not just avoiding execution, right? It's not going to bulk up your instructions. Like I think that was a good mechanism because I like the idea of in debug builds having more checking, and in production builds you're okay with a null pointer exception if there's a true mistake.
Yeah, and that's true, and that's one of the things with check and require where I'm always on the fence about it, and I have had discussions with some folks on the Compose team about it. It's good to add those checks and requires in a lot of places, but sometimes, we can be a little too diligent. And if you're always testing something that should basically never happen unless you're debugging, like maybe don't have it.
Yeah, so what we have in Lint, I don't know how widely it's used anymore, I still use it, is you can check if assertions are enabled. And to do that, well, there's some Java code which basically asserts false and traps it, right? So we can determine whether assertions are on.
Nice.
And we do more expensive checking only if assertions are on. So it's one thing to check the range of your arguments, fine. Although C++ runs faster because it doesn't bother with that stuff, right? But things like making sure that data structure, for example, isn't circular, that is a cost that you want from your tests.
Yeah. And
you want maybe in your debug builds, but you don't want every user to pay that price.
No, yeah, absolutely not. Yeah, no, you have to be careful about the cost, the cost of those checks. And again, like for check and require, it's less about the test. It's more about the amount of code that get generated at the call side. Like for instance, when I see a piece of code and there's a loop and inside it does like 4 checks in a row, and I know that it inlines all that extra code, it's gonna hurt. And again, maybe it doesn't matter for the code you write, but if you're going over every pixel of a bitmap, don't do that. Or use a version of check that doesn't inline all that stuff. And so you need to write benchmarks. You need to look at the generated code to truly understand what's going on. It's a never-ending fight.
Yeah, and so you've gone through about a year now, right, of sort of looking at every possible thing to make compose faster and faster. And we're seeing that in the benchmarks for
Yeah, well, and to be clear, engineers on the Compose team are working on the much bigger optimizations that give us a lot more than those macro optimizations, right? Like I've been focusing on macro optimizations for a couple of reasons. One, I find it interesting.
Yes.
And B, it's something where I can do this whenever I have time, and they add up together, but we have bigger bottlenecks that other smarter people are taking care of.
Everything is guided by profiling.
Right. Like I think a good example, like strong skipping in the compiler, massive performance improvements, much more important than all those macro optimizations. So we have folks doing much more interesting work.
One thing I thought was interesting that you did was the scatter map, right? So looking at making a more performant map. And like in the IntelliJ code base a while back, I mean, they had some custom collections, and I think they're more and more being switched out by something called fast-util. And these are all, I think, primarily avoiding autoboxing. I think that's the main reason they exist. You have some ints, you want to put them in a map, you don't want to do autoboxing. But I think scatter map does more than that. Like it's really trying to deal with cache locality and avoiding sort of putting entry objects all over the heap. Do you want to say more about this?
So the world of hash maps is fascinating because depending on what you're doing with the map, like there are different ways to implement a hash map that can be better suited for your needs or not. And the standard map that's used by Kotlin and in Java. So when you do mutable map of in Kotlin, it creates a linked hash map. I have two problems with that. One, a linked hash map maintains the insertion order. So when you iterate over it,
which I love, but
when that's what you want.
Yes, but I normally will directly construct hash map myself because I don't want it. But every now and then when you want that order, it's so nice to go, give me a link.
It's nice to have it. What I don't like is that when you say mutable map of, it returns the signature returns a map interface. Yeah. Great. The problem is that since that function has always returned a linked hash map, now all the code out there might be relying on the fact that the insertion order is preserved.
I'm sure they do, yeah.
So now you're paying the cost for this abstraction of going through an interface, but there can only ever be one implementation because if we change the implementation in the Kotlin standard library, we're going to break a ton of code out there. And what I don't like about maintaining the insertion order when it's done on your behalf is that it might hide bugs that you're not aware of. Like for instance,
I think mutable map of as a constructor, I don't think it actually lets you specify an initial size.
It doesn't, and that's my other pet peeve.
Exactly, and that's why I tend to avoid it, because it's one of those habits of mine that sure, if it's a tiny map, don't worry about it. But if you think you're going to put thousands of elements in or more.
But see, on the opposite side of the spectrum, I've seen a lot of hash maps in C++, for instance, where what they do is when you compile in debug mode, they poison the hashes with, let's say, the current time or the build number, so that every time you run in debug, you get a different structure.
Yeah, that's smart.
To catch bugs.
I think we've discovered in Lint unit tests that there seems to be, like at least for hash map, there are differences in hashing between Windows and other OSs. Mm-hmm. So every now and then it'll fail on Windows because someone was not sorting the keys, and so so you do get it automatically if you run a multiple operating system.
But anyway, so by default, mutable map of gives you a linked hash map, and forget the exact details. You can watch my talk, but basically the way a hash map and specifically a linked hash map are implemented in Java runtimes or on Android is every entry in the map is wrapped into. Is part of an object. It creates an actual map.entry, which contains a number of pointers. So those things are actually pretty heavy. So,
very frequently, code will access those objects directly. They're exposed as part of the .entries method. And so before destructuring, this is what you would do. You would basically iterate through the entries, and you could call get key and get value together.
And that was the right thing to do in the world of Java, because, before lambdas, right? That was the right way of doing that. But what happens that not only do you spare a lot of cost in terms of memory, I forget, but let's say the overhead is something like 40 bytes per entry. If all you're storing in your map are ints or booleans, you have many times more metadata than you have actual data. So that has a cost. And then when you traverse or when you access the map, like every time you insert, there's an allocation. Every time you traverse, you do multiple pointer jumps, which, depending on what you're doing, can be costly. But in the compose runtime, we do a lot of iteration of the maps, and suddenly data locality is terrible because you're jumping through all those pointers. So the goal of scatter map, it basically uses a technique that's called open addressing. So there's an array that contains the keys, an array that contains the values, and then there's an array of what's called metadata, and the overhead is 1 byte per entry. So it never allocates unless it has to resize the arrays. And if you iterate over the map, so there's a for each that uses a lambda, so it gives you the key and value directly, it's just gonna go through the arrays in order as they're laid out in memory. So it's like as fast as it can be in terms of memory locality.
And do you preserve iteration order?
It does not preserve iteration order, okay. Insertion order. Yeah, that's part of it. And also, it does not implement the map interface. And the reason for that is the map interface in Kotlin that we inherit a lot of the Java one, has a lot of APIs that are very memory unfriendly.
But what if you were to, because I saw that and I thought, because I was very excited when I saw your benchmarks. Like, this is fast for the uses I know we have many of. You have significantly better performance. The only one that it's slower is removal, which was only slightly worse. And removal is something we actually don't do a lot in the cases I'm thinking of. And I was thinking, we should have switched to this. But the not being a map is kind of a problem. And then I thought, hey, there are built-in maps that just don't support some of the API methods. If you call them, they'll throw unsupported operations saying, don't do this. Like, I think remove, for example, is one of the optional operations. So I was thinking that if you were to implement map, many clients will not be calling one of those methods. You find it hard to support. So what if you did have a
bridge? That's something I should look into. There is a bridge where you can call that as map.
Yeah, but I don't want to pay the price unless someone calls the unsupported method, right? That's the whole key.
But I mean, what you can do is that you can call as map once and just wraps the scatter map for you, and then you can use it as a regular map.
And that then supports all the operations?
It supports all the operations. So there, it's up to you to, if you call, some of those operations like dot entries.
It's going to be very expensive. Because I was just thinking that if you were to directly implement it, I want to pass your map to some libraries that may be taking a map, right? And I know they're only going to insert. So I'm fine.
That's why the as map exists.
Yes, but I would like to not pay that price.
Yeah, but remember, you go from 1 allocation per insert to 1 allocation to do an as map. So it's still a win.
Yes.
Right.
All right. I will play with it.
Yeah. You should.
It's just I can imagine now as doing a pull request, right? Where I'm basically replacing some places. We're just going to initialize this. But if at a bunch of places that map is used, I have to start calling .asMap. Or you're saying I should do it at the initialization?
You can do it initialization and see if it works.
Okay.
And scatter map is based almost entirely on a library from Google called Absol, which is a C++ library. And one of the
based as in ported, not as in wrapping.
Ported, yeah.
Okay, yeah.
So it's all written in Kotlin. And one of the really cool things that it does is, because you have this open addressing, right? Like there's no buckets like in linked hash map. So you may have collisions to resolve in the array. And the way it's implemented, it can actually look at 8 entries at a time to find a correct insertion point. So it's super efficient algorithmically as well.
Yeah, no, I was excited to use it. And then I got to the point of, it doesn't implement collections.
You should try it and measure and see what happens.
Well, I'm sure the numbers will be good. I'm trying to make it a small diff. Right. If you had assertion order, we can maybe make a case for it replacing the mutable map of.
Well, do you need the insertion order to be preserved?
No, because in most places we need that. We actually construct linked.
Right. So, yeah. Don't preserve the insertion order.
Yeah. So this has been a lot of talk about micro optimizations, and maybe I want to re-emphasize that we both understand that there's a time for it and there's a time that you don't do it. But
yeah, and if you look at, I wrote a bunch of blog posts on some of the things I've been doing, and I'm always, because that's the first thing that comes up in comments. Like people are like, "Oh, you shouldn't do this." Like, yes, I know, and we all know, but 2 things. One is you might be writing code someday where you need to do this kind of work, and also it helps understand how things work. So it's not because you're not going to use it that you shouldn't learn from it, right? And I think learning the techniques, learning the tools, learning how to understand what happens under the hood, and it's very complicated, right? Like I'm by no means an expert in any of that. And I'm still shocked sometimes when I write those benchmarks and I make those optimizations. I'm like, okay, I have fewer instructions and I think I'm doing better memory access. Oh, look, it's not faster or it's slower than before.
It's sometimes like if you go back to your example of iterating through the pixels, you're going to use a profile and it's going to say, oh yeah, this is hot. You're like, well, of course it is.
Yeah.
But you're not going to get the insight that actually, if we reorder this, we're going to get twice the performance, right? So I think it's a good muscle to exercise, right? Is to think about what happens behind the scenes. What is the actual architecture? It's not just a black box.
Yes, absolutely. Yeah, and also the thing is like with Kotlin and Java, sometimes you feel like you're fighting the language a little bit because there's a lot, even today, like when I do those optimizations, I get to a point where I look at the assembly and I still see instructions that don't have to be there. But I can't remove them because I don't have the language for it. It doesn't let me, it's protecting me too much. Yeah. I'm like, just leave me alone.
And so I think when you have this mindset, and then you learn how a large language model works, you're a little horrified.
Well,
right? They're kind of...
Well, in a way, large language models are very optimized. They just multiply matrices. Like, yes. It's pretty fast.
Yeah.
But yeah, I think it's good to understand like what the compilers do or not, and don't just throw casually like, oh, the VM or the runtime will take care of it or the compiler will take care of it, because it might not. Also, interestingly, if you ever write benchmarks for your app, knowing what the compilers do will help you write better benchmarks, because those compilers sometimes, especially R8 and the ahead of time compiler or the JIT, are good at getting rid of work that doesn't need to happen. And I still get bit by that regularly, where I write a benchmark, a micro benchmark. I'm like, oh wait, that feels a little too fast. I'm like, wait a minute. Oh yeah, the compiler just removed all the code. And so silly thing, right? But when you write a micro benchmark loop, make sure that whatever you're doing inside the loop, that's the easiest way to do it, has side effects. So you can just, usually what I do is that I get the output of whatever work I'm doing and I increment a counter based on that value. And then I print the value at the end of the benchmark, just so that the compiler cannot remove the code. Because if you don't do that, and there's a loop that does work, but doesn't do
and you want to make sure it's a small amount of work, so you're getting a true measure of the speed up.
Yeah, but like for instance, if you're doing code that computes a tree, maybe what I do is I take the size of the tree and I just add it to a counter.
Yeah, I just meant that if you were to sleep 500 in the loop, then you wouldn't see a speed up because it's going to be dwarfed by your computation.
But yeah, so sometimes like that's also the difficulty with optimizations. You're not always doing what you think you're doing.
Yeah, benchmarking is tricky. One of the difficulties you highlighted in your talk again. So this sounds like an ad for your talk.
Everybody should watch the talk.
Yes.
It's called Practical Optimizations. It was at Android Makers 2024. It's on YouTube.
Yeah. Is that in a benchmark, you were comparing linked hash map with scatter map.
Mm-hmm.
And the benchmark is basically going and inserting a bunch of stuff into the linked hash map. And so when you were comparing iteration speed, this was like the best scenario that map could get. In reality, the linked hash map might sort of accumulate objects from all over the heap from being inserted at different times. Whereas in a benchmark, you're doing a very targeted thing, which gives it locality that in reality it wouldn't have.
Yeah.
So it was its best fight against scattermap, which of course is guaranteeing that coherence.
Yeah, and you make a good point, right? Like when you write a benchmark, since you're not running the whole app, you're probably not gonna have GC runs. Your object, when you allocate them, they're gonna be close to each other in memory. So like it's not what's going to happen. And that's why you need micro benchmark and macro benchmarks. And that's what we do in Compose, right? When we do those optimizations, we test them at a micro level, and then we validate that it's actually having an impact on layout, measure, draw, all that stuff.
Yeah. Any new optimizations you're working on?
I was working on something. I just came back from vacation. I was working on something before I left on vacation. I forgot. But since then, I read an interesting paper on a better eviction strategy for LRU caches. So I might take a stab at implementing that, because I think we use an LRU cache in a few places in Compose. So might be a good...
If you need more homework, your article on Scattermap promised a part 2.
Yes, I know. I have a long list of topics that I want to cover because it's a lot of interesting stuff.
Yeah.
I just need, to do it.
Yeah. A couple of these things that you've run into, I remember when you were working on your performance talk, you're like, hey, this should be a lint check. And I think I worked on one, and then we discovered that actually art inlines it or something. So it was kind of pointless.
It was one of those cases where between art, like it's difficult to, like we won't be able to know ahead of time if it's going to go away or not.
Yeah.
And therefore we can't really write a lint check because...
Yeah. But if you think of anything else, send it my way.
We just need a lint checker that looks at the final ARM code.
Well, so you were connecting to a real device to pull the so is that specific to ARM, or would this work, when you have other chips as well? Are you just calling like ADB and pulling some?
So yeah, it's calling ADB, so it would work with any Android device. But I gotta say, I don't look at anything other than ARM, because the reality is that today, Android devices are basically ARM. There might be x86 devices out there, but when you look at the instruction sets, they're so similar anyway. Like,
there isn't a chipset that's doing something dramatically different where you're going to have to make a trade-off.
There used to be, maybe there's still MIPS like in Android TV or things like that, but again, I don't expect.
We had x86 at some point, and
x86 MIPS, RISC-V. I don't know if there are devices shipping RISC-V out there, but I don't know what the status of that is. So anyway, in the end, those things are very similar at the assembly level instructions. So,
anything else?
A lot, but I could go on and on and on. We'll talk about it again, and maybe in another version we'll talk about more specific things.
We're probably going to talk about it over lunch right now, right?
This sounds good.
Yeah, cool. All right. Thanks, everybody.
Thank you, Tor.